Okay, welcome everyone to today's seminar on automorphic forms. So it's a pleasure to have Hasan Saad from LSU, and he'll talk about Atkin and Swinnerton-Dyer congruences for meromorphic modular forms. So Hasan, please.
And hello, everyone. First, I want to thank the organizers for giving me the chance to give this talk. And today I'll be telling you about recent joint work with Michael Allen and Ling Long on Atkin and Swinnerton-Dyer congruences for meromorphic modular forms. And before I get into that, let me start with something more classical and well-known. Okay. So consider the delta function, this product q times product from n equal 1 to infinity of 1 minus q to the n of 24. If we write the Fourier coefficients as tau of n, this tau, the Riemannian tau function, it satisfies some well-known linear recurrence relations. If you take p to be a prime and n bigger than or equal to 1, then tau of Pn is tau of p times tau of n minus p to the 11 times tau of n over p. And the natural question is, well, do such recurrences hold for general Q series? Well, if the Q series are the Q expansions of holomorphic modular forms, of course, the answer is yes. This was proven by Hecke. So just recall, if you take a congruent subgroup gamma 0 n of SL2Z, then the space of cusp forms of weight K, it has a certain basis, that's called F1 up till Fd, where if you write out the Fourier series of any of the elements of this basis, they satisfy similar recurrence relations as before, namely, and I'm writing in this form because I will be using this form later. If you take M or S to be bigger than or equal to 1 for almost all primes P, then A of MPS minus A of P times A of MPS minus 1 plus PK minus 1, A MPS minus 2 is exactly equal to 0. And the general outline of what Hecke proved, or how Hecke proved it, is as follows. Well, he constructed for almost all primes these Hecke operators, some linear operators on the space of weight K cusp forms. And this space happens to be finite dimensional, and these linear operators for different primes, they commute. And therefore, if you just do a simultaneous diagonalization and look at what the TP does to the Fourier series, then you get exactly the following recurrence relations. And natural question is, well, what if we consider more general modular forms? So for example, instead of thinking about holomorphic modular forms on congruent subgroups, what if we consider them on non-congruent subgroups with finite index? What happens instead of considering holomorphic modular forms, I allow poles at the cusp, so I consider these weakly holomorphic modular forms. And what if I allow myself to take poles on the upper half plane, so actual meromorphic modular forms? Well, there's a couple of problems with trying to apply Hecke's proof to any of these situations. For example, for non-congruent subgroups, Berger proved that the Hecke operators act trivially on the non-congruence part. For the weakly holomorphic modular forms, the space is infinite dimensional. And for the meromorphic modular forms, the situation is even worse. The Hecke operator doesn't even preserve the location of the pole. And Atkin, does that mean there's no arithmetic information to be gained? Well, the answer is no. And to this end, Atkin and Swinnerton-Dyer conjectured that we should look at p-adic recurrence relations. So let me show you an example before I talk about that. Take E4 to be the Eisenstein series of weight 4, and consider the following modular form, E4 to the 6 over delta minus 1464 E4Q. So this is what I'm calling a weakly holomorphic cusp form. So it's holomorphic on the upper half plane. It has a pole of order 1 at the cusp. It's of weight 12 on SL2Z, and the constant term vanishes. That's what I mean with weakly holomorphic cusp. Okay, so as you can see, the Fourier coefficients grow, well, as you can see from the first one, it grows really fast. So a linear recurrence relation is just not going to happen. However, if you take p to be a prime, bigger than or equal to 11, and some integer n with p to the s dividing n, you have that a n of p minus tau of p times a of n plus p to the 11 a of n over p. Not exactly 0, but it is 0 modulo p to the 11s. So modulo power of a prime, which depends on how divisible n is by that prime. And of course, the other difference is this is not a of p, but it's tau of p. Okay, so is this just a coincidence, or is it an example of a more general phenomenon? So this is an example of the so-called ASD congruences. And Scholl and Kazalinsky studied this, and before I show the result, let me just introduce some notation. So take gamma to be a finite index subgroup of SL2Z. We're going to denote the space of weakly holomorphic modular forms of weight K by MK Sharik gamma. And if Z is a cusp of gamma, we're going to denote by TZ an appropriate local uniformizer near Z. Now, if gamma was a congruent subgroup, this will just be the usual Q if you're looking at the cusp at infinity. Okay, and now if I give you a weakly holomorphic modular form, I'm going to call it a cusp form or a weakly holomorphic cusp form. If at every cusp you take the Q or T expansion and the constant term vanishes, and the space of such weakly holomorphic cusp forms, we're going to denote it by SK Sharik gamma. And finally, we're going to need this arithmetic condition. So take P to be, if we have P to be a prime, and ZQ is the ring of integers in a finite unramified extension of QP. So let's say it's just ZP. We're going to call our weakly holomorphic cusp form exact if for all the n which are negative, AF of n is divisible by n to the k minus 1 in the p-adic integers. And we're going to denote the space of these exact weakly holomorphic cusp forms by SK Sharik exact. Also, please feel free to stop me at any time if you have any questions. In this notation, this is what Scholl and Kazalinsky proved. So first, for the holomorphic part on non-congruent subgroups, take gamma to be a finite index subgroup with some geometric conditions. And Scholl proved that for weights bigger than or equal to 3 and almost all primes, there exists some polynomial with integer coefficients, such that if you take any cusp form, so holomorphic cusp form, on this finite index subgroup with coefficients in ZQ, and you act as if those t, the variable of the polynomial, is pk minus 1 times vp, and you plug the coefficients in. So what that means is I plug in AFMP to the S next to A0. Here, next to A1, I plug P to the K minus 1, and I subtract the power of P from from the Fourier coefficient. And I keep doing this and add everything up. I will get 0 modulo P to the K minus 1 times S plus 1. And this polynomial is not random. In fact, it comes from some of the analytic representations by Deligne attached to modular forms. And from that, you have that this polynomial has roots being algebraic integers, and their absolute values are p to the k minus 1 over 2 under any embedding of the algebraic integers into C. So they're k minus 1 Weyl numbers. And the degree of this polynomial is 2 times the dimension of the space of holomorphic cusp. Okay. And moreover, and this was by Scholl, Kazalinsky and Scholl showed that you can take a weakly holomorphic cusp form instead, and everything would still work, except you'd need to require the cusp form to be exact. So you need to impose some conditions on the principal parts, and the congruence is somewhat weaker. It's p to the k minus 1 times s. So this is what Scholl and Kazalinsky proved. And the question is, well, what if we allow poles on the upper half plane? So let me start with some examples. So take K, and this was a conjectural example by Zhang. Take K to be 4, 6, 8, 10, or 14. So the weights where the space of modular forms in SL2Z is just spanned by Eisenstein series. And take C over Q to be any CM elliptic curve such that the J invariant is not 0 or 1728. Now, to each of these weights and to each of these CM elliptic curves, we're going to associate the following modular form. So EK tau over J tau minus the J invariant of the elliptic curve. Now, this vanishes at the cusps. It's of weight K, and it has a pole exactly at the points tau where J of tau equals J of C. And if you take P to be any ordinary prime of C, such that the J invariant is not 0 or 1728 mod P, and you take any MS to be bigger than or equal to 1, then in fact we obtain 2-term recurrence relations for these Fourier coefficients. So you have A of MP to the S is equal to some number times AM. Some number does not depend on M, times AMPS minus 1 modulo P to the K minus 1S. Moreover, this number, it's not random. It's a p-adic unit, and it's the p-adic unit that solves this equation. So you reduce the curve mod P, you count the number of points, you subtract that from P plus 1, and you take the p-adic unit solution to this. Or in other words, because P is ordinary, the Frobenius is acting on the L-adic Tate module. It has two eigenvalues. One of them is a p-adic unit, and that's the UPC that appears here. And let me show you another example. So take the group gamma 1, 4, and consider the following half module given by some eta quotients and the usual theta function, the sum of q to the n squared, and define the two following modular forms of weight 3. So f is essentially theta squared times lambda prime over lambda minus 2, and g is f times lambda plus 2 over lambda minus 2. So these modular forms, again, they vanish at all the cusps, and they have poles of order 1 and 2 respectively at lambda equal 2. And if we look at their Fourier coefficients, they also satisfy two-term recurrence relations. So if you take P to be bigger than or equal to 5, P is equal to 1 mod 4, and that means the prime is ordinary for some elliptic curve, which I will show you in a bit, and M has to be bigger than or equal to 1, then AF of MP to the S is equal to some number times AF MPS minus 1. AG MP to the S is equal to P over that number times AG MPS minus 1, and this equality is modulo P to the 2S. And these mu's, they're also the p-adic unit roots. So just as before, the eigenvalue of the Frobenius on the Tate module, which is a p-adic unit, for the following elliptic curve, the Legendre elliptic curve y squared equal x, x minus 1, x minus 2. Okay, so I've shown you two examples where you have two-term recurrence relations, and does that generally happen if I take a meromorphic modular forms? Well, the answer is no. But if you allow yourself to take longer recurrence relations, just like as in Scholl and Keseliski, the answer is actually yes. And moreover, in special cases, these long p-adic recurrence relations, in a way, they specialize to two-term recurrence relations. And this special case, as I will show later, it relates to a certain elliptic curve related to the pole having a CM structure. So the y squared equal x, x minus 1, x minus 2, it has CM by z adjoint I. And in the conjecture of Zhang, the C over Q is assumed to have CM. All right. So just to introduce some notation before I show you our main result, take gamma to be and this is essentially the gist of our work. Take gamma to be a subgroup of finite index in SL2Z. I'm going to denote by x gamma and y gamma the algebraic curves h bar, so h with the cusp adjoined modulo gamma, and the by y the affine subspace, so just h modulo gamma, the upper half plane modulo gamma. And from now on, the capital letter K is going to denote an algebraic number field over which the modular curve is defined. Okay, and this Gothic Q is going to denote some finite subset of the affine subspace H modulo gamma. So essentially the locations of the poles. And there's some appropriate capital M bigger than or equal to 1. And we're going to denote by this SK gamma comma star U comma OK adjoint 1 over M. So this is going to denote the space of meromorphic modular forms. Their poles are supported on this Gothic Q. They have to vanish at the cusps, and the Fourier coefficients lie in the ring of integers of K up to division by some powers of M. Okay, we're going to denote by minus or G of F, the maximal pole order of F. So I look at all the poles and choose the maximal order that appears. And we have this letter D, which was the degree before, but now it's going to be 2 times the dimension of the space of cusp forms, plus, so the 2 times the dimension of space of holomorphic cusp forms, plus K minus 1 times the number of pole locations. And if P is a prime, I'm going to denote by Kp the p-adic completion of K. And if Kp over Qp is unramified, we write R to be the degree of the field extension. Also, this Kp and R appear in Scholl-Keseliski's work, but I swept it under the rug for simplicity earlier. Okay. So in this notation, this is what we show. Take gamma to be a subgroup of finite index in SL2Z with, again, some geometric conditions such that X and mu are defined over K. And for almost all primes, we show that, again, there's a polynomial of degree D with integer coefficients, such that if you take any meromorphic cusp form and any ms bigger than or equal to 1, the following occurs. You do the same thing as before. You plug in, again, this R, it appears before in Sholin-Kazalitsky's work, but we can ignore it. These gammas, again, you just think of them as one if you're working with congruent subgroups. And again, you do the same recurrence as before, AF of MP to the S over P to the I, and this will be equal to 0 with, so this is essentially the same as in Sholin-Kazalitsky's work, except for one important difference. It's not modulo P to the K minus 1S, but rather there's a shift that comes from the poles. And maybe let me say a little bit about this. This shift works in two ways. If you have no holomorphic cusp forms and the pole order is somewhat small, then the shift gives you a stronger congruence relation. And the strength of, or the extra strength of this congruence is you take the weight and you subtract the maximal pole order. On the other hand, if you have holomorphic cusp forms or the pole orders are large, then the congruence is actually weaker. And it's weaker as follows. You take the maximal pole order, you subtract 1, you take the factorial of that, and it's weaker by depending on how many p's divide that factorial. Moreover, this gamma p, which again we can ignore, we can just not think about, is just some element of kp which depends on p and gamma. This really comes from which uniformizer you choose for non-congruent subgroups. Okay, so this is what we prove. So we prove we have an analog of essentially a collective p-adic recurrence relation for meromorphic modular forms. And we're going to show in some cases it reduces to two-term recurrence relations. But before I tell you about that, let me say a bit more about this polynomial. So this polynomial decomposes into two pieces. It decomposes into one piece, which has nothing to do with the poles. And for each pole, you end up with an extra pole contribution. Now, this piece, which is independent of the poles, it has degree 2 times the dimension of the space of holomorphic cusp forms. And in fact, it's exactly the polynomial that shows up in Sholin-Kazalitsky's work. And for each of these poles, here's how the extra contribution works. So there's this thing called a universal elliptic curve. So it's a family of curves over this modular curve y gamma. If you take the specialization, so essentially plug in u for the parameter, this extra polynomial comes from there as follows. You take the eigenvalues of the Frobenius, you plug them in this way, and you multiply by p to the r. Now, what I mean, where this comes from, or how to think of this, is as follows. When you take the fiber where the pole is located, you get an elliptic curve. It has an ellatic Tate module and a Frobenius action on that Tate module. And because the Frobenius action acts on that Tate module, it acts on the k minus second symmetric power of that Tate module. And this is the characteristic polynomial there with an extra twist, by adding this p to the r, or the so-called the Tate twist. All right, so let me talk about how the CM action now comes into play. Suppose you have no holomorphic cusp forms, and EU is a CM elliptic curve by some imaginary quadratic subfield of K. So just enlarge the field capital K if necessary. And we show there exists some modular forms. So they're meromorphic, again, poles supported on U with the Fourier coefficients, just enlarging the M, so to speak. And there's k minus 1 of these modular forms. And now the two-term recurrence relation is slightly more complicated. If you take P to be a prime and M has to be bigger than or equal to 1, you have a relation between AUI, MPS minus 1, and AU of possibly some other modular form out of this family at MP to the S. And let me just say something about this. This sigma is the Frobenius endomorphism of KP. the CUIs, we know something about their divisibility properties. And this sigma tilde, it works in two ways. If the Frobenius endomorphism fixes the CM field, then this sigma tilde I does nothing. So you get a two-term recurrence relation on FU comma I. And otherwise, you get a relation between the coefficients of FUI and f of k minus 2 minus I. So you get a relation between two Fourier coefficients of this family. Okay, and these CUIs, yes, we know something about their divisibility properties, but we also know something more. If you plug in the CUIs into this weird formula over here, you get some DUIs, and if you plug them here, they solve the following equation. So all that to say is the CUIs are related to the point counts on elliptic curves, just as before. And in fact, if let's say sigma fixes the CM field, so for some some primes in an arithmetic progression, we know exactly what the CUIs are. But because this relationship is complicated, and I've shown you two examples of two-term recurrence relations, let me show you an example where the sigma tilde or the sigma does not fix the CM field. So let's go back to the example from before. Take P to be a prime bigger than 5, and I'm going to consider the same weight-free modular forms as before. If P is 1 mod 4 and MS bigger than or equal to 1, again, this is the two-term recurrence relation I showed you. But if you take P equal 3 modulo 4, things get somewhat more interesting. Okay, I'll say what I mean with numerically, but you can see that AF of MP to the S is related to AG MPS minus 1, not to AF MPS minus 1. And AG MP to the S is again related to AF MPS minus 1. Now, the equation I showed you before, it doesn't necessarily determine what these CUIs are, but we know they satisfy a certain equation. And these P mu P over 4 AF1 over AG1 and the other one, they satisfy this relation. And let me just tell you what this mu P is. And now nothing here is a p-adic unit because the P is a super singular prime, so both eigenvalues of Frobenius are not p-adic units. But this mu P numerically, we conjecture that it's given as follows. So it's a Legendre character times some values of the p-adic gamma function evaluated as such. Okay. So these are the two-term. So this is an example of the two-term recurrences we show. And moreover, what we do is, so again, I said there's this special family which has these two-term recurrence relations. Well, we find explicit method as an algebraic formula to compute all these forms for weight 3 and 4 for the group gamma 1, 4, as long as the poles are located at CM points of the Legendre elliptic curve. So that's our special family, or the universal elliptic curve, so to speak. And the example I showed you by Zhang, it's part of a more general conjecture for SL2Z, and we prove these conjectures, which I will mention at the end, except at small primes, although we can extend it to some small primes, except possibly at p equal 2, which we don't know how to show. And the methods we use to find these modular forms or special modular forms explicitly, they can be generalized to all genus 0 finite index subgroups of SL2Z, provided you're willing to work with somewhat annoying explicit computations. Right, so this is essentially what we show. This is the gist of our work. And now I want to get to talk about the methods or the method of proof that we use. So again, we had a couple of problems before. We had the Hecke operators. They act non-trivially, or they act trivially in the non-congruous part. They don't preserve the location of the pole, and so on. So how do we overcome these analytic limitations to obtain our required arithmetic information on the Fourier coefficients? And the answer is to not view these modular forms as analytic objects, but to view them as geometric objects. And I will spend some time talking about that. And I'll start off with the question, well, what is a modular form? Well, here's some alternative characterization that shows up in a first course in modular forms. So a modular form of weight k, it's actually a function on lattices, lambda in C, such that the following happens. If you take lambda to be the lattice z plus z tau, where tau is in the upper half plane, this defines a holomorphic function on the upper half plane. Here I'm talking about holomorphic modular forms of level 1. Moreover, the transformation property, the modularity property, it can be described as follows. F of mu lambda is mu to the negative k times f of lambda for all mu in C star. And we require that f of z tau plus z is bounded as the imaginary part of tau goes to infinity. And this is already a step in the direction of looking at modular forms geometrically. And that's because if I look at lattices, well, each lattice, it corresponds to an elliptic curve and a non-zero holomorphic differential form on this elliptic curve. And this correspondence goes as follows. You take a lattice. For each of these lattices, I can take C modulo the lattice. That's my elliptic curve. And if the coordinate on C was W, well, dW is a non-zero holomorphic differential form. Or in other words, if you take the equation of the elliptic curves given by these various P functions, being the x and y, well, the differential form is just dx over y. Okay, so let me rephrase the above definition in terms of this correspondence. And of course, this is well known, and I copied some of these things from a course by Caligari. Okay, so a modular form of weight k, it's a function on pairs of lattices with differential forms on them, such that f of e comma mu omega is mu to the negative k f of e omega with some holomorphicity conditions. Okay. And I want to say something about this. Given f differential dw on c over z plus z tau, as you apply the Mobius transformation on tau, the dw changes from c tau to c tau plus d times dw. So if you take dw, let's say, to the power k, and you apply a Mobius transformation, it changes c tau plus d to the k, dw to the k. And on the other hand, if this c tau plus d is your mu, from the modular form, you'll have a c tau plus d to the negative k. So the opposite of what happens to d tau. So in other words, we can think of a modular form as a correction term for dw to the k to descend from something defined on h to something defined on h modulo gamma. And this is already a very geometric picture that does not really depend on C. Because elliptic curves and differential forms on them, you don't need analysis for that. And, well, correction terms, I will talk about that in a bit. Okay, but let me just now rephrase the picture we just described. So take E to be the unit, so it's some family of elliptic curves over y1n, so h modulo gamma 1n. You could think about that as just C over z plus z tau as you mod out by gamma 1n. Now, there's a line bundle or a sheaf algebraically such that at each point in this modular curve, if you look at the fiber of this line bundle or the stock of this line bundle, it's just the vector space of holomorphic differential forms on the elliptic curve at that point. Okay, so if I want to talk about I want to view a modular form as a correction term for when this, when the dw descends to this y1n, then in other words, that means a weakly holomorphic modular form. And I say weakly holomorphic because we're just talking about y1n now. It's a global section of bold omega to the k. Moreover, if I want to talk about holomorphic modular forms, well, this line bundle or sheaf, bold omega, it has this canonical extension to x1n, and a holomorphic modular form is just a section over the full or the proper modular curve. Okay. And for n equal 4, let me just to show you relate this to what we did before. This x1n is just a projective line, and the universal elliptic curve is the Legendre family, y squared equal x, x minus 1, x minus lambda. So for each lambda and x1n, this is what the elliptic curve looks like above us. And this is why it showed up when we were talking about the recurrence relations for gamma 1,4. Just to be accurate, this is not really true for n less than or equal to 5. We need stacks, but this is really the picture. Okay, so I've given you, or I've recalled for you maybe, a geometric way to look at modular forms, but there's another geometric way of looking at them that's, more common in a course on modular form, where a cusp form of even weight k, it's just a global section, or a differential form f tau times d tau to the power k over 2. So are these really two different pictures, or are they the same view? And it turns out they are actually the exact same thing. This is due to something called the Kodaira-Spencer isomorphism. So if we take omega x1 log z to be the sheaf of meromorphic differential forms on the modular curve with poles of order 1 supported on the cusps. So this is essentially the d tau above, and there's no reference to any universal elliptic curve. Then this bold omega squared, so modular forms of weight 2, explained as the way I mentioned earlier. And the omega x1 log z, which is the definition above, they are isomorphic as sheaves, so they give you exactly the same geometric point of view. So let me just maybe say a little bit more. So a modular form of weight 2, holomorphic at the cusp, is just f tau d tau, where f of tau is bounded. And if you look from the point of view of the cusp, well, d tau is essentially dq over q. So locally, this is fq dq over q. So if fq is it has a constant term, well, at the cusp, this means the differential form has a pole of order 1. And that's why we needed the logarithmic poles above, or poles of order 1. So if I need so intuitively, of course, the bold omega is the square root of the above way of looking at differential forms. And moreover, if I want a cusp form, well, I want fq dq over q to not have q in the denominator. So I want to remove this log z if I want a cusp form of weight 2. And if I want a cusp form of weight k, well, it's just a global section of this little bold omega k minus 2, or times, or tensor product with this omega x1 without the log z. And that's what a cusp form of weight k is. Of course, here k has to be bigger than or equal to 2. All right, so this is the geometric picture for modular forms. You can do this over rings without needing to do analysis or working over C. And I want to talk a little bit about differential operators on these modular forms. So to do that, I'm going to talk, and again, I will relate this to something classical. So if I just want to recall, if we have an elliptic curve given by the following equation, the de Rham cohomology is essentially r dx over y plus rx dx over y. So again, you don't need this modular exact forms. And over C, this just as follows. If E is C over Z plus Z tau, and X and Y are the versus P function and derivative of the versus P function, then your dW and rho W, or PW dW, are exactly what spans the de Rham cohomology. And that means it's just the differential forms of the second kind with poles of order, which means poles of order at most 2 at the cusps. Okay. And just as before, this bold omega allowed me to view the differential forms on this family of elliptic curves, we have the same thing for the de Rham cohomologies. There's this vector bundle on X, and at each fiber away from the cusps, it is the de Rham cohomology of the elliptic curve at that fiber. And this is where the differential operator comes into play. So I can take derivatives of dx over y as dx over y varies over a family. So given any derivation on y, for example, let's think about it as d over d tau, we have a derivative of the de Rham cohomology classes as they vary. And this means there's some connection. Of course, you can extend this to X by a result of Deligne. We have some connection from the bundle of Dyrem cohomology to the bundle of Dyrem cohomology tensored with omega x1 log C. So just to show you an example of this, again, take n equal 4, you have this Legendre elliptic curve. If you take the Dyrem cohomology of that, and you take the derivative del over del lambda, where lambda is the half module, then you have the following differential equation in the Dyrem cohomology. And if you replace dx over y by the period, which is 2f1, the hypergeometric function with upper parameters 1/2 and lower parameter 1, then this is exactly the hypergeometric differential equation, or the Picard-Fuchs differential equation. So this is really not mysterious. However, I want to talk a little bit, I want to say something about how this behaves at the cusps. So this is a result by Katz. At the cusp, this canonical extension, it has a basis omega canonical and C canonical, which is the derivative by d over d tau of omega canonical. And the differential equation is as follows. So if I differentiate omega canonical twice with respect to d over d tau, I just get 0. Okay, so how does this relate to the more classical differential operators on modular forms? Well, if G is a modular form of negative weight, 2 minus k, so if you differentiate a modular form, it's not generally a modular form, but if I differentiate it k minus 1 times, this ends up being a modular form of weight k. And you can prove this by just a direct computation. So how does this relate to the setting we just showed? So to show you this, let's take the following chain complex. So take ek minus 2 to be the k minus second symmetric power of E. So E is essentially bold omega plus the dual of bold omega, so modular forms of weight 1 and negative 1, so to speak. So you raise it to some powers, you get things of varying weight. And this chain complex, just take that, differentiate, and so you get the image of this derivative, so to speak, and you get ek minus 2 tensor omega x1. And if you take the cohomology of this chain complex, or rather the hypercohomology, so essentially closed modulo exact, Scholl and Keseliski proved that this hypercohomology is the space of exact weakly holomorphic cusp forms on gamma 1n modulo the images of the image of the Ball operator acting on the weight 2 minus k weakly holomorphic modular forms. And of course, over C, this is just this exact, we don't need it. Actually, we don't need over any field really. And the difference is just an arithmetic condition when we want to work over ZP, for example. So again, this Gauss-Menin connection, this nabla here, and this chain complex, they relate to things like the Ball operator, which show up in the classical theory of modular forms. Okay, so let's extend this to the meromorphic setting. So take a finite collection of poles and consider the following chain complex. So we just modified the previous chain complex by allowing poles of order 1 at the poles where, you know, the meromorphic modular forms are supposed to blow up at. And we showed that the hypercohomology of this is the space of meromorphic cusp forms with poles supported on U modulo the image of the Ball operator acting on meromorphic modular forms with poles supported at U. And this isomorphism, it's not really true. It's only true over a field. Over a ring, it's a somewhat more complicated condition than being exact. So the left-hand side is or the hypercohomology is a subset of the right-hand side, but that subset is expressed very explicitly in terms of Fourier coefficients and pole orders. All right. So far I've told you about differential operators, or actually maybe I showed you about differential operators on meromorphic modular forms, and we've described those geometrically without really needing to reference analysis or the complex numbers, so we can do this over ZP, but we still haven't talked about a replacement for the TP. And this replacement was found by Scholl. He essentially showed that the tau goes to p tau, so the V operator there's essentially a way to define it on this hypercohomology, even though you don't have an upper half plane. And this is what he really showed. For almost all primes, you get a Frobenius operator acting on the hypercohomology, and this tensor ZP really just means view the Fourier coefficients as elements of ZP instead of as elements of Q or Z. And the Frobenius operator acts as follows. So you take a Fourier series. It's literally just a p to the k minus 1 times a VP operator. But this is because you're working on hypercohomology. So again, you have this modulo images of the Ball operators. This Frobenius acts as such modulo the Ball operator acting on arbitrary Q series with coefficients in ZP. So to just put all of this together kind of quickly, you have this Frobenius. It acts as a VP operator. And the hypercohomology is actually finite dimensional. And Scholl finds what this characteristic polynomial of the Frobenius is. So if you apply it to an element of the hypercohomology, you get 0. So again, you apply it to modular form or a weakly holomorphic modular form, you get a 0 in the hypercohomology, which means whatever expression you got in terms of Q is 0 modulo the image of this Ball operator. And if you just write this out, you get exactly the p-adic recurrence relation that Scholl and Kazalitsky proved. Okay, so let's extend this to the meromorphic setting. We have a following short exact sequence. So this is Scholl's and Kazalitsky's hypercohomology. So weakly holomorphic modular cusp forms modulo Ball operator. This thing in the middle is meromorphic cusp forms modulo Ball operator. And the last thing is so you take every pole location, you look at the Durham cohomology of the fiber above, and you take the k minus second symmetric power. And the Frobenius is defined by Scholl. It extends to our setting. And on these fibers, so again, there's k minus second symmetric powers of the Durham cohomology. So the Frobenius acts as the k minus second symmetric power on the Tate module, twisted by P. So it's really simple. And because you have this short exact sequence, the characteristic polynomial of Frobenius, which we need to figure out the form of the recurrence relation, it's the characteristic polynomial on the left times the characteristic polynomial on each symmetric power, as you go over all the poles. Again, with a twist, of course. All right, so let me say a little bit about what the maps and the short exact. So if you put all this together, you get our general theorem, the general recurrence relation for meromorphic cusp. To go to the CM or the two-term recurrence relations, let me say a little bit more. So what are these maps? Well, for the first map, you have weakly holomorphic cusp forms and meromorphic modular forms. But in fact, these weakly holomorphic cusp forms, I can do another identification of this hypercohomology with modular forms with poles supported on U and certain conditions under a principal parse. These conditions are quite restrictive, and what they are is, if you look at the Laurent series locally, it must look as if it came from the image of a Ball operator. And for the second map, it's essentially a residue map, and explicitly it's given as follows. So you take your meromorphic modular form, and you take, let's say the pole is located at W modulo gamma, where W is a point in the upper half plane. So you write the following expression, where capital X and capital Y are indeterminates. You write that out, you take the residue, you get an expression in terms of this capital X and Y, and of W, of course. And you just send it to this, and this is what the residue looks like in the symmetric power of the Durham cohomology at the fiber. All right, so if we put all this, well, let me show you how to prove the CM two-term recurrence relations. So assume the dimension of the cusp forms is 0. The hypercohomology, it has dimension 2 times the dimension of the space of cusp forms. So there's no the hypercohomology of Scholl and Kazalitsky is just 0. So the short exact sequence means that this residue map, and now I'm assuming one pole just for simplicity, it's actually an isomorphism. But if EU is a CM elliptic curve, the Durham cohomology has an action of CM, so the k minus second symmetric power has an action of CM, and because the residue is as an isomorphism, the hypercohomology inherits a CM action. And the Frobenius it turns out to commute with the CM action. So if I diagonalize with respect to the CM, I end up diagonalizing with respect to the Frobenius. And so here's the strategy for the corollary or the two-term recurrence relations. You find a CM basis for the Dremke homology, if you want to do this explicitly. From there, you just do some linear algebra and get a CM basis for the k minus second symmetric power. And you find pre-images of the residue map for the CM basis, and these will be eigenvectors of Frobenius, which means they will satisfy the two-term recurrence relations I've shown. Okay, so for the last 4 minutes, let me give you an example of this strategy. So I'm gonna give the conjecture by Zhang and then tell you how we prove it. So first, let me recall, if you have k to be an integer and f is some function on h, the raising operator is rk comma tau f of tau is given by the following expression where I of tau means the imaginary part of tau. And if I write rk to the power r, I don't mean compose it r times, I mean do rk of tau, then do rk plus 2 of tau, and so on r times. And the point of this is, if you start with a modular form of weight k, so something satisfying the modularity property, you apply the raising operator, you get something modular of weight k plus 2, of course, at the expense of losing holomorphicity. Okay, and here's the conjecture by Zhang. He says take ABC to be integers. GCD is 1, D is B squared minus 4AC, and alpha D the CM point in the upper half plane, and suppose the J function is not 0 or 1728. And consider the following explicit elliptic curve. And for each prime P, if it is good and has ordinary reduction, let mu B be the p-adic unit root of this elliptic curve. And he considers the following modular forms. So for each k in 4, 6, 8, 10, 14, and this alpha D, he associates, and for each r bigger in this range, he says do the following. Take this auxiliary variable z, write the following expression, apply the raising operator r times, plug in alpha D for z, and then multiply that by ek tau. So if you do this, you get a meromorphic modular form of weight k for SL2z. It vanishes at the cusp, and it has a pole of order exactly r plus 1 at j of tau equals j at the point alpha d, or alpha d mod gamma. And he conjectures that they satisfy the following two-term recurrence relation. So this is the two-term recurrence relation he conjectures. He doesn't put the condition p divides k minus 2 factorial. That's just the condition we're able to prove the theorem with. And I think we can do this for all odd primes, for all odd primes really, with some modifications, which we didn't really write down. And here's how we prove it. Consider his basis. Now, because he gives us this expression, this explicit construction, do some calculus, raising operator, write things out, and take the residue and view it as this analytical thing on this elliptic curve, and then rewrite it in terms of the Weierstrass P function. And I want to know if whatever expression I wrote is an exact differential form. So what we do, or it's this eigenvalue of Cm. So I apply the eigenvalue, I subtract it from the differential form, and it has vanishing periods and poles of order at most 2. So it means it vanishes in the Dremke homology, and therefore this is exact. So they're actually pre-images of things, or the modular forms he shows are pre-images of things which are eigenvectors of Cm, and therefore, putting all this together, everything follows. So just to summarize, we proved a generic ASD type congruence for meromorphic modular form. We showed it reduces to two-term recurrence relations under some conditions, and we give explicit methods to compute these special modular forms with two-term recurrence relations. Thank you.